So now that we've gone over what streams are, we've talked a bit about what parallel streams are. I showed you what minuscule changes are necessary in order to convert a sequential stream to a parallel stream for our search stream gang example. Now what we're going to do is we're going to start taking a look at the internals of parallel streams. So we'll talk about the different ways that streams work under the hood. And the first part of the discussion here, we'll talk about things that you can change, things that you can control through various knobs and options you can set versus things that you can't change. There's some stuff you can change, some stuff you can't change. The first question, of course, is why do you care, right? Why do you care how streams works under the hood? And at one level, converting from a sequential stream to a parallel stream is often just as easy as changing .stream to .parallel stream, so that seems pretty straightforward. But why would you actually be interested in knowing what happens under the hood? Well, the reason is because it'll make you a better streams programmer in general. So if you understand how things work under the hood, then when performance matters, which, let's face it, if you're using parallel streams, it's probably because you want things to run faster, then knowing how things work internally will make you more effective at programming. Whereas if you only understand how the APIs are defined, then it may be harder to know how to tune it. It may be harder to understand why all of a sudden when you switch from a sequential stream to a parallel stream, your performance goes down, which is always sort of embarrassing because you think you should speed things up. So once you understand a bit more about how things work under the hood, it'll be a lot easier to program and get the performance gains that you're looking for. If you recall, there are 3 phases of a Java 8 parallel stream. So first, there's the splitting phase, which uses a splitterator to partition the stream elements up into multiple chunks. So you've seen a couple of examples of that. We'll take a look at a more detailed example of how to split things up later in this discussion. There's the apply phase, where the chunks that are split by the splitterator get handed off to the common fork join pool where they can run in parallel. And then the final phase is the combine phase. So that's the part that starts when the terminal operation is reached, and if you recall, that'll start pulling the source of data from the data source through the intermediate operations. Those things are run in parallel, and then as they finish running in parallel, they get joined together and combined by the final phase. Okay, and it's important to understand which of these phases you can control and which ones you can't. So some of the phases you have very little control over. Other phases you have tremendous amount of control over. So for example, you can control how things get split. You can also control how things combine. As it turns out, controlling how things get applied is harder because that's really done for you under the hood. But there are some things you can do to influence how the apply phase works as well. Now, out of the box, the splitting and thread pool mechanisms used by a parallel stream are often invisible. They're like a ninja, right? You don't actually see them unless they want to be seen. All the Java collections that are predefined in the Java class library come with splitterators out of the box. So we've talked about that before. We talked about how you can have a splitterator, which splits things up. And as you can see, the collection interface itself has some default methods that handle splitterating and also handle streams. And then subclasses of collection like array list or hash map or tree set or whatnot can handle the splitting in different ways. There's also a way of being able to use the splitterator when a stream is created, either a parallel stream or a sequential stream. Likewise, out of the box, the common fork join pool is used. And there's some ways to get around this, but they're really a big hack, so we won't talk about them. We'll talk more about how you can configure the common fork join pool for the streams framework for parallel streams in much the same way that you can do it for the fork join pool itself. So the common fork join pool, if you recall, can be programmatically modified by either setting a system property or using a managed blocker. And that same set of techniques also applies when you're dealing with parallel streams. So you get stuff out of the box that works, but if you want to customize it, you can. And so one way is to define your own splitterator. Doesn't really make a lot of sense, honestly, to define your own splitterator for the built-in types. Might as well use the ones that they give you out of the box. But if you make your own collections, you make your own classes, like our phrase match split iterator, which we'll look at later, then it does actually make sense to define a split iterator, because you may have special custom ways of splitting things up into chunks. And then, as we talked about before, there's this managed blocker, which can be used to control the number of threads in a pool. So let's talk a bit about ordering. So if you recall, remember there's the split, apply, combine phases. And the apply phase is the part where processing takes place. So that's where things actually get run in the fork join pool. And it turns out, by design, the order in which the chunks are processed in the fork join pool, where the chunks are the things your split iterator is creating, or somebody's split iterator is creating for you, that is intentionally meant to be non-deterministic. And what that's just a fancy way of saying you have no control over it, and it's intentionally designed to run by whatever means makes the most sense to the fork join pool, the operating system kernel, the underlying hardware cores, et cetera, et cetera. Programmers have little or no control over how these chunks are processed. So you just have to suck it up and deal with it, because you're not going to be able to control that one way or the other. Why is it done this way? Well, the reason for doing it this way is it gives lots more opportunities for the underlying software and hardware and the infrastructure to manage how optimization takes place. So because you have no control over it, it can do things that you probably wouldn't really understand as an application developer. It knows the size of the underlying cores. It knows the size of the underlying instruction and data caches in the underlying cores, or somebody does. The fork join pool can do all kinds of clever things, as we saw before, to do work stealing in order to try to make sure all the cores are kept as busy as possible. So by taking that out of your hands, the system can do a more effective job of optimizing things that you might otherwise struggle with and probably get wrong, because you don't have as much experience, perhaps, as the people who built the infrastructure, software and hardware. So that's actually a good thing. Interestingly enough, even though the ordering of the processing is non-deterministic, you do in fact have some control over the results in which the processing is given back to you. And that may seem a little bit odd. It's like things can run in any order, but you do in fact have the ability to control how the results are presented to you. And as it turns out, you can actually control that quite a bit. And so we'll be talking about how you could control that. The order, what's called encounter order, the order is maintained. The order of the output will match the order in which the data input is encountered under certain circumstances. And I'll give you the overview, and then we'll talk about this in more detail, because it's kind of important to understand this. The output order is maintained, or what's called the encounter order. That's the order in which the original input came in. If the source is ordered and the aggregate operations that are used are obliged to maintain the order. Okay, that probably doesn't help at all. It doesn't explain anything. So I'll go into that and talk about it in more detail. If you want to get another take on this, take a look at the link here by Brian Getz, where he talks about encounter order. So remember, we've been talking before about encounter order, and I mentioned with things like an array list, for example, the data comes in a particular order. So let's assume, for sake of argument, that we've got the works of Shakespeare, and let's say that we are going to read them in alphabetical order. So, As You Like It comes before Hamlet, comes before Julius Caesar, comes before Macbeth, right? Let's just assume they're alphabetically ordered. So if that's the order in which the input comes in, then irrespective of the order in which the processing takes place on those various plays of Shakespeare, the output will come out in the order that the input came in. That's the encounter order. So if the input source is ordered and the aggregate operations don't modify anything with respect to the ordering, then you'll keep the same order on the output. And this doesn't really matter whether the stream is parallel or sequential, although honestly, if it's sequential, it's pretty obvious it's going to be in counter order because there's no non-determinism at all. It's only if it's parallel that there will be non-determinism. So here are some things that will respect encounter order. So ordered split iterators, ordered collections, static stream factory methods, these are all things that will respect the encounter order. So let's take a quick look at an example. Let's assume that we've got ourselves a list. So you can see we have arrays as lists, and let's say the list is like 1, 2, 3, 4, just monotonically increasing integers up to n. And so we're going to store that as a list of integer. And this will be stored under the hood as an array list. So that's the encounter order, is the order in which the stuff came in. What we're going to do now is we're going to take that input list and we're going to, in parallel, process all the elements in the list from 1, 2, 3, 4 up to n. And what we're going to do here is we're going to go ahead and we're going to filter out all of the odd numbers. So we're going to only filter even numbers. We're only going to keep the even numbers. So if x mod 2 equals 0, that means it's an even number. So we're going to keep that one. Then we're going to go ahead and multiply the result by 2. And then we're going to go ahead and store this into an array. So you can see that the last thing is toArray, and we go ahead and make a new array. And the result of that processing must be 2, 4, 6, 8, 10, etc. And that's because the output must correspond to or must comply with the encounter order. Even though the processing of any of those elements could have run non-deterministically in some other order. For something as easy as this, it's a little hard to understand why it would run out of order, but when we get to more complicated things, you'll see why it could run out of order. So the point is, because this is an ordered collection, because an array list is an ordered collection, then the output must respect the encounter order. Conversely, unordered collections don't need to respect encounter order. So here we're going to take the original list. You can see we have 1, 2, 3, 4, ... up to n. And we're going to make ourselves a hash set of the original input. And as you might expect, if you recall from the data structures course that you undoubtedly took somewhere, hopefully here or elsewhere, the hashing doesn't really have an order. So it just hashes the numbers wherever they go. So there's no particular reason why you need to keep them in some kind of encounter order. They're just sort of pseudo-randomly distributed through the hash set. So when we take that hash set and we say .parallel stream, then in that case, the output doesn't have to follow the encounter order. And in fact, the code may run faster because the streams framework doesn't have to ensure that the output order matches the input order, the encounter order. So when it runs, it'll just take whatever results come out and it'll just put them into the output array, and whatever finishes first. Whereas the other case, we had to kind of rearrange them to fit into the encounter order. And if you want to play around with this kind of stuff, take a look at the EX21 folder in my GitHub live lessons repository, and you can play around with all these things and see how it works. It's really cool. It's really quite instructive to run these things and notice how sometimes you get deterministic results. If you use ordered collections, then you'll get kind of non-deterministic results if you don't. So unordered collections don't need to respect encounter order. Therefore, the system can be optimized by the underlying fork join pool, which runs in parallel and can let the system decide what to run and when to run it and where to run it most efficiently on which cores. Likewise, certain intermediate operations also affect ordering behavior. So if you recall, intermediate operations include things like map and filter and flat map and so on. Certain of the intermediate operations will affect the ordering behavior. And that's because certain of the operations are so-called stateful. And what stateful basically means is that some operations have to keep track of what's happened up to that point in order to be able to provide the right semantics. So as you can see here, things like sorted, skip, limit, and so on. Those operations will kind of affect the way in which parallel processing takes place. We'll talk more about this later, but things like sorted imply that there's kind of a barrier that occurs, and if you see the sorted intermediate operation in a stream, that means that everything up to that point could run in parallel, but then the results have to be coalesced and sorted before the next phase of processing can take place in later operations in the stream. Which makes sense, right? You have to wait till you get all the results before you can sort them. There are other operations here, such as distinct, such as limit, which also have an impact on the semantics of things. And again, if you were to run this code, what you would discover is that even though the results here have to be ordered, because we have the array list, which will be an ordered collection, using distinct, which just means get rid of any duplicates, and using limit will greatly slow things down, because then the system has to do a lot of other things under the hood in order to obey those semantics. So distinct has to go through, for example, and see, are there any duplicates in the input? And if so, get rid of them. So that's another stateful operation. And limit has to keep track of how many things you've already processed, so it can stop you after you've exceeded the limit. Interestingly enough, if we take the same stream, so here was the stream before, and we'd make one little tweak to it, and we change it to unordered, then what that tells the stream is, even though the input is ordered, even though I have an array list as the input, which by default is ordered, if you put the .unordered intermediate operation, it's an indication to the system, don't worry about ordering, run this thing faster. So it'll incur less overhead, so it'll run faster than it did before. Certain terminal operations also affect ordering behavior, and this is kind of an interesting one. You'll see that there's one terminal operation called for each ordered, which I show you here. I'll walk through the code in a second. And as the name implies, this gives you ordered output, where the ordering must match the encounter order. And I'll go back and walk through that in a second. Here's the same, more or less the same code, except this time we use the .forEach method or terminal operation. And in this case, the semantics are unordered. So by default, for each is unordered, whereas for each ordered is ordered. So let's take a look at the example and see what it's doing and why does it matter. So what we've got here is we've got an array list, which is an array list initially. And then we're going to create ourselves a queue, and this is a concurrent linked queue. So a concurrent linked queue is simply a queue that can have elements added to it by multiple threads at the same time, and internally it has a lock so it doesn't end up corrupting the state of the queue, which is a little bit like your synchronized array, which we'll talk about here in a second for the assignment 2A, or 2B, sorry. So what we do then is we go through a parallel streams. We've got multiple threads that are running in parallel. We filter, we map, we limit. So we're doing a bunch of stuff. And at the end, we do for each ordered. And you see we say q : add. So q : add is a thread-safe add method that will not have to worry about corrupting the internal state of the queue, since it's a concurrent linked queue. And for each ordered, we'll make sure that we put things into the output in the same order that they came in the input. So once again, it'll be 2, 4, 6, 8, 10, or whatever. But it'll run in different threads. Conversely, the for each method is unordered. So there's no reason for the system to put it in the same encounter order. So you might end up with 10, 2, 6, 4, 8. It doesn't matter what the order is. I mean, obviously, you have to get the right semantic results of filtering out the odd numbers and then multiplying the other ones by 2. But you're not going to end up with having problems. You'll have the right results, but they may not be ordered in the encounter order. Okay, so that's the end of the first section of the parallel streams internals. And the main point here is really just that there's some things you can control. You can control the output because you have ordered collections, or you use operations that, or you include aggregate operations that respect ordering and terminal operations that respect ordering. Or you can have unordered stuff, in which case it'll typically run faster, but the order will not respect the encounter order.